Hi everyone, welcome back to ChipVerse. I hope you liked the previous video about RISC-V processor. If you didn't see that video, I will provide link description and video will available in end cards. Today's topic is ASIC design flow. This is a fundamental concept for many students and anyone planning a career in VLSI. Let's understand the step-by-step process of how an ASIC, which stands for Application-Specific Integrated Circuit, is designed and eventually becomes a working chip. What is an ASIC? An ASIC is an application-specific integrated circuit. It is a chip designed specifically to perform one particular task. For example, the camera processor in a smartphone or the controller in a washing machine. Unlike general-purpose chips, an ASIC is custom-built for one function. That's why it operates faster and uses less power. Major phases of ASIC design flow. The ASIC design flow consists of two main stages: front-end logical design, back-end physical design. Let's break down each stage in simple terms. In front-end logical design, specifications. The very first step is to define what the chip should do, its speed, power consumption, and area requirements. For example, our chip should process a camera image in 0.1 seconds and use a maximum of 2 watts of power. Architecture design. Based on the requirements, the system is divided into blocks such as ALU, memory, controller, data path, control logic, and interconnections. This forms the backbone of the design. RTL design. Next, designers write the logic in hardware description languages, HDL, like Verilog or VHDL. This is called Register Transfer Level, RTL design, where you describe how the chip's operations take place during runtime. RTL verification. Once the code is ready, verification begins using simulations and test benches. Technologies like System Verilog and UVM are used to check for bugs and fix them. This step ensures the design works correctly before moving to synthesis. Back-end physical design. Synthesis. After verification, the RTL code is converted into a gate-level netlist using standard cell libraries. This is done automatically by software. The netlist is optimized for timing, area, and power requirements. DFT, designed for testability. Special logic like scan chains and built-in self-test, BISD, are added to make it easy to test the chip after manufacturing. Floor plan. A physical layout plan is created, deciding where blocks go, how signals connect, and allocating power grids and I/O pins. CTS, clock tree synthesis. The clock signals must reach every block in the chip simultaneously. So a balanced clock distribution network is designed. Placement. Standard cells and blocks are placed physically in the right locations on the chip to ensure signals travel in the shortest paths and timing issues are avoided. Routing. Connections between blocks and cells are made using metal wires. Signal integrity and timing rules are strictly followed. Sign-off and fabrication. After all steps, final verification is performed, including timing analysis, power analysis, and design rule checks, DRC and LVS. Once the design is approved, it is sent to a silicon foundry where the physical chip is manufactured on silicon wafers. Packaging and testing. The manufactured die is cut out, placed in suitable packaging, and tested for functionality and reliability. Only chips that pass these tests are released to the market. Conclusion. This is how an ASIC chip transforms from an idea into a working integrated circuit. Every stage requires detailed work, teamwork, patience, and strong technical knowledge. If you enjoyed this video, don't forget to like, share, and subscribe. Let me know your suggestions for future topics in the comments.